screen?
Yeah, just press this presentation button. Yeah, it's
Right.
coming up all right. Yeah.
Okay. So is it necessary to switch on my camera, or is it sufficient to show my slides only?
No, the slides are good enough.
Okay, so you see the title of my talk, quantum speed limit time, non-Markovianity, and quantum phase transition of spin systems. So that reflect, I'll be talking about the quantum speed limit time of quantum mechanical system interacting with a driven spin environment, and we'll use the system as a probe for studying the dynamics or the characteristic behavior of the driven spin environment. So like to introduce me, this talk comes from ComStats University, Islamabad, and that's my name, Dr. Salman Khan Saifi. And this work, in fact, constitutes what complete chapter of my PhD student, Mr. Muhammad Musaddiq. And this was published last year in Journal of Physics and Mathematical and Theoretical with GUI given over here. I would like to in the first part, I have in fact divided my talk into two parts. The first part focusing the newcomers or the students and will therefore provide the background of quantum mechanics from the perspective of quantum information theory. And the second part, and the first part almost spent half of my talk. And the second part would be very technical and only the expert would be able to follow it. So I would like to begin from the definition of a qubit. Any quantum mechanical system lives in two-dimensional Hilbert space is called a qubit. And the dimension in this presentation or in this talk would refer to the energy levels. For mathematical purposes, these energy levels are written in the form of kits, which can also be written in the form of column matrices. And the 0 bit would refer to ground state of the qubit, and the excited state would refer to, the 1 kit would refer to the excited state of the qubit. Therefore, the Hilbert space is spanned by the two energy levels, that is ground and 1. Now, if this qubit is in the vicinity of an environment, there is chances that the environment may affect the dynamics of the qubit and both interact with each other. This interaction may be unwanted sometimes, or this may be deliberate. In the case of deliberate interaction, the environment may be in the control of the experimenter. In the case of unwanted environment, the environment is totally out of our control. Then the environment can be modeled from classical perspective. In that case, the environment can be characterized with the help of some stochastic variables or through some set of stochastic variable or random variables. And it can also be modeled in the form of the quantum mechanical entities. In that case, the environment consists of a large number of quantum mechanical systems where each quantum mechanical particle or system is described through some set of quantum mechanical operators. Since it consists of very large number of particles, therefore the dimension of the Hilbert space of the environment is generally very large. And I am representing that with a subscript I, where I in fact represent numbers which correspond to different dimension. And the I equals 0 would in this talk refer to the ground state of the environment. When the interaction takes place, then the qubit or the system in the environment are treated jointly. And for that purpose, a joint Hilbert space is constituted from the individual Hilbert spaces through tensor product. And the basis vector of the joint Hilbert space then is written in the form of composite kits like 0 EI and 1 EI. And these are in fact the tensor products of the two basis vectors, that is the basis vectors of qubit and the basis vectors of environment. Okay. Now, it is easier usually to describe the dynamics of a composite system or open quantum system through density matrix formalism. And I would like to introduce the density matrix for a single qubit first, and then we'll try to comment on which kind of processes when environment entry can take place. So density matrix is in fact an operator which is written in the form of outer product of the state vector. And for a qubit, a most general state vector can be expressed as a superposition of the two basis vector or the two energy levels, where A1 and A2 are probability amplitudes and may be complex and they satisfy the normalization condition. That is, the sum of the modulus square of the probability amplitude is always 1, which reflects that the modulus square of the probability amplitude is in fact the probability of finding the particle in that energy level. So substituting the value of state vector in this bra in the definition of density matrix, we can put it straight away into this form. You may note that I have put the static over here and have written the case in the form of bra that correspond to the bra of psi. And removing the brackets, I can then put it into this form. So this form is fair enough. But in order to understand some characteristic properties of the qubit, I would like to put this into matrix form by plugging in the column matrix in the row matrix form of the basis vectors. So if I do that, I can put the density matrix into this form. Now, there are two types of elements of the density matrix, the diagonal ones and the off-diagonal one. The diagonal ones are obvious that there are just probability of finding the qubit in either the 0 state or in the 1 state, but the off-diagonal elements are called coherence. And this term arises because of the superposition in the initial state. If there were no superposition in the initial state, there would not be these elements. Now, it depends on how the qubit interact with an environment. Two different types of processes can take place. For example, if the environment could affect the all the elements this way, where Gx is a function consists of the parameters of the environment, then we call such a process as relaxation. And we see that for relaxation, usually we always consider the qubit to be either in the superposition state or in the excited state. For example, if the qubit is prepared in the ground state initially with only the probability amplitude A1 and A2 equals 0, all the rest three elements will go to 0. And if that goes to 0, this term will also go to 0, and there will be no effect of the environment on the qubit. However, if it is either in the superposition state or is prepared in the excited state initially, then we would have this element and this element over here. And so the relaxation process would take place. It is conditional for relaxation process to either prepare the qubit in superposition state initially or to prepare it in the excited state. On the other hand, if the environment change the density matrix or affect only the off-diagonal elements through a function where again f of x, the chi is some parameter of the environment. In this particular case, only the off-diagonal elements are affected, and in most cases, this is an exponential decay process. We call this process dephasing or phase damping. And a dephasing process or an environment that causes dephasing and put the qubit into a mixture state, thereby vanishing the coherence terms or killing the coherence term and putting it only in a probabilistic mixture of different possibilities or states. In this talk, I would focus, in the technical part of this talk, I'll focus on dephasing processes. That is, I'll consider an environment which can cause dephasing of the state of the qubit. And then I'll use the qubit as a probe to investigate the dynamics of the environment, because the environment imprints its effect to the off-diagonal elements. In these imprinted information over the space of the cuboid can be used to extract some useful information about the properties or characteristic of the environment. And that's what I'll be doing in the technical part of this talk. So the next thing comes how the states of qubit evolves. We know from Schrodinger wave equation that a unitary operator acts on the initial state, evolving it to some final state. And in the density matrix formalism, the same thing is done through this one equation, where we put the density matrix in between the unitary operator and its complex conjugate, and we get the final density matrix. And the unitary density matrix is obtained from the Hamiltonian of the system. And writing it in this form, I definitely put H bar equal to 1. So in the case of open quantum systems, we prepare the initial density matrix of the composite system as the tensor product of the density matrix of the particle or qubit and the density matrix of the environment. And the environment is generally considered to be in its ground state. Under this perspective, substituting this value of the initial density matrix into this one form, I can write the final density matrix into this form. Now, this is obviously when the environment is unwanted, that means it is not in our control. We are unable to find the total density matrix or to deal with the total density matrix. So what we do, we partially trace over the dimension of the environment and getting the reduced dynamics or the reduced density matrix of the qubit, and that is carried through this one equation by just partial tracing over the final density matrix of the composite system and getting the reduced density matrix of the environment. So I use these quantifiers. This equation quantifies this quantum speed limit time, and here the parameter, this is the relative probability, which is described in terms of the trace of the product of the final initial density matrix. Tardy in this case correspond to the drive time, and the quantities in the denominators is in fact average over the drive time, and therefore these are the eigenvalue or the square roots of the eigenvalues of the final initial density matrix. And this quantifier was published in this paper in I think 2014. So this is the DOI of the paper, which presents this form of potential time. Then I use the non-Markovinity equation, which is given by this one relation. This is this equation measures the non-Markovinity on the environment. The integrand in this case is in fact the derivative of the half of the trace norm of the difference of the two density matrix. That is the derivative of D, where D is defined in terms of the trace norm of the density matrices. I'm writing here rho 1 and rho 2. And these rho 1 and rho 2 are in fact these conditional density matrices that maximizes the integrand. There are two conditions on this integral. We see one is the maximization, that is we consider a pair of initial density matrices that maximizes this whole integral, and then we count only those distances for which the derivative is positive, sigma is positive. And the trace norm is defined by this one equation. So where rho 1 S2 and at this position is, or at these two positions are obtained through a superoperator or non-unitary dynamics of the initial density matrices. Then the non-Markovian, if the value of n t is greater than 0, the environment is said to be non-Markovian, and if it is equal to 0, it is said to be Markovian. Non-Markovianity in fact correspond to the flow of information from the environment to the system, and Markovian in fact refers to the flow of information from system to the environment. So in non-Markovian case, both flow, that is from the system to the environment and from the environment to the system, can take place, whereas in Markovian dynamics, the flow of information is one-dimensional, and with the passage of time, the qubit loses all the information according to it in the form of coherence. So the off-diagonal elements goes to 0. This definition of the non-Markovinity we have taken from Brewer and Pelu, which was published in 2009 in PRA. Okay, with that said, the next thing is quantum phase transition. We are familiar with two types of phase transitions. One classical phase transition that is carried by the change of temperature. With the change of temperature, a particular value of this changes the chemical potential of this object or the bonding energy, and a phase transition takes place. That particular temperature is called critical temperature. On the other and we have quantum phase transition that is taking place at theoretically absolute zero temperature. So there is no thermal agitation in the system, and the transition is carried by varying some parameters in the Hamiltonian, which results in certain symmetry breaking of the system, and that value of the parameter is then called critical value of the parameter. So I'm representing here with lambda sub c. Okay, now let's move on to the technical part of the environment. I consider a qubit, and the qubit is surrounded by a number of spins, which I call Ising spins, such that the nearest neighbor interacts with each other through an interaction constant J. Then every spins of the environment interacts with the central qubit with a string delta Q. And finally, as we switch on an applied magnetic field that interacts only with the spins of the Ising spins, or with the spins of the environment. This whole picture can be put into this equation, where this term gives the free dynamics of the central qubit. This gives the interaction between the nearest neighbor spins. This is the interaction between the spins of the environment with the magnetic field lambda. And this is the interaction between the spins of the environment and the qubit. Okay. This Hamiltonian can be put into diagonal form, but first I would like to comment on the Hamiltonian split into two branches. One part represents the dynamics of the qubits when it is in the ground state, and the other part represents the dynamics of the qubit when it is in the excited state. So I represent them with HG and HE. We apply Jordan-Wagner transformation, which links the spin operators with fermion operators, satisfying the fermion intercommutation relation sigma xl, sigma y, and sigma z, and am on the fermionic operators. And then we did this is in position space and applying Fourier transform to take them into momentum space with operator dk and d minus k. And then finally applying Bogoliubov transformation to diagonalize the Hamiltonian, where the Bogoliubov operators beta alpha are linked through this one relation with the Fourier transformation, and the theta or Bogoliubov angle and is given by this one relation. Obviously, all the parameters of the spin enter into theta. And using these values, the Hamiltonians can be put into this form, which is now diagonalized. And E alpha k is the energy spectrum, which can be written for the ground state and excited state into this one form. When delta is 0, it is the ground state energy spectrum, and when delta is present for other values than 0, then it gives the energy spectrum of the excited state. So using these values in the formalism that I developed in the previous slides. So if I consider the initial state to be a superposition like this for the qubit, and using the formalism I developed, I can write the final composite density metric, the final reduced density metric into this form, where we see that the off-diagonal elements are multiplied with this parameter phi alpha, which is explicitly given by this one relation. So we are these are the energy spectrum of the two levels in eta k is written in terms of the Bogoliubov angle. Okay, the modulus square of this phase factor is our decoherence factor is called Loschmidt echo, and the dynamics of the Loschmidt echo was studied in this paper for this Hamiltonian. We will study the dynamics of the quantum speed limit time and the non-Markovinity, it's straightforward to put the quantum speed limit time into this form, where most part we see in the equation that depends on two things: the initial state angle and on the phase factor or the dephasing parameter, and on non-Markovinity. And this relation I simplified to non-Markovinity, where again the non-Markovinity is totally phase dependent term. So what we do, we now want to simulate our results for non-Markovinity and quantum speed limit time. This equation, this figure gives the red curve gives the non-Markovinity with values on the right ordinate, and the other one gives the quantum speed limit time. The important thing is that to the left of lambda is equal to 1, the non-Markovinity is monotonically decreasing, and in the vicinity of lambda equal to 1, it becomes 0, which means that at this position, the environment is purely Markovian, while to the left of this value, it is non-Markovian. And then there is a sharp increase in its value, which shows some sort of non-analyticity in the behavior of non-Markovinity. And this plot is taken for n equal to 100 spins in the environment, with other parameters set to this value. There is an oscillatory behavior in the quantum speed limit time to the left of lambda equal to 1, and that oscillatory behavior vanishes to the right. If we change the number of spin, I increase it to this, there is a change in the behavior of quantum speed limit time in the vicinity of lambda, and a little oscillation to the left of, to the right of lambda equal to 1. We simulate that for different number of spin to tell n is equal to 800. So what we see an abrupt change in the vicinity of lambda equal to 1, both in non-Markovinity and quantum speed limit time. The non-analyticity or the non-analytic or the abrupt change in the value of non-Markovinity may suggest that this is some sort of this may reflect some sort of phase change, whereas in the case of quantum speed limit time, this is the non-analyticity to the left of lambda equal to 1 is not obvious. However, to the right, it is a sharply decreasing and maybe may reflect some non-analyticity in the behavior. Nevertheless, to impose that this is really a phase transition, we need to apply another criteria. And before coming to that criteria, I would like to present the behavior of the two quantities. This is what quantum speed limit time against the drive time and the applied distant of magnetic field. We see that for low value of the magnetic field, the quantum speed limit time increases with the drive time. However, in the large range, it sharply decreases to the left, it is oscillating, and to the right, the oscillation almost dies out, or with very small amplitude. However, there is again a decrease in the overall behavior of the quantum speed limit time to the left of lambda is equal to 1, if I say this whole region. And here is the strength of the coupling between the qubit and the environment. And again, we see in oscillatory behavior with lambda, but different types of behavior with delta. And if I present the same, the plots between same parameter for non-Markovinity, there is a non-Markovinity in the strong field. There is no almost the system is Markovian for small range of the T. However, it is non-Markovian in the weak field region. Weak, I say, for lambda lesser than 1. And again, at lambda is equal to 1, there is a hum or a non-analytic behavior in the non-Markovinity. And this is another behavior for between this is not tardy, this is in fact delta. So I have this mistake. This is again delta, the strength between the coupling of system and environment. So let us see whether this hum in the non-Markovinity definitely represent a phase transition of the system. For that, we need to find the derivative of non-Markovinity, and we see that as the number of spin increases in the environment, the derivative goes to becomes some sort of goes to show a divergent behavior. And if I plot the maximum of the derivative of non-Markovinity, the maximum for different number of spin, I get a scaling behavior. And this scaling behavior is in fact a verification of the phase transition. So the non-Markovinity is capable to signal the phase transition in the system, where we have plotted in this for the logarithm of the derivative of non-Markovinity with respect to applied magnetic field in the logarithm of the number of spin. So this is a justification that a non-Markovinity can signal quantum phase transition and Ising spin. And this quantum phase transition is from, in fact, from the basis of, is obvious from the Hamiltonian, which takes from the basis of sigma z operator to the basis of sigma x operator, that is from computational basis into the maximally superposed basis or plus minus basis. So what we conclude from the study, what we concluded from the study are there's both non-Markovinity and quiescent time can detect quantum phase transition in the neighborhood of quantum critical point of the environment. So these quantity adds to the list of quantum quantifiers that measure quantum phase transitions, such as entanglement, quantum discard. And the final one, which is very encouraging, is this one: a strongly driven environment with large number of spins has potential capacity for quantum speed up. So the evolution can be sped up. And thanks. I think I finished with the time. I haven't taken longer. Dr. Freya.
No, excellent. And thank you very much, Dr. Salman, for a very good presentation that also considered students by giving introduction to density matrices in the beginning as well. So thank you for the presentation. We have one question in the chat. Let me read it out for you. Any idea what will happen if you go beyond pure dephasing?
If you go beyond?
If you go beyond pure dephasing.
Mostly, so far as I have studied and I have worked in the spin environment, all the spin environments induce dephasing. I haven't seen any example which causes relaxation. However, in the bosonic environment, yes, there is relaxation. And we have published a paper in that case, which is Dickey model. And in that case, there is relaxation processes, and obviously the quantum speed, and we have studied quantum speed limit time and non-Markovinity in that case as well. The paper was published in, what is that? I forgot the name, American, so I forgot the name, but yeah, both the quantities signals quantum phase transition even if the environment is bosonic and which induces relaxation processes. So that is not dephasing, and here we have found that it can correctly segment quantum phase transition.
Okay. So another question is, can you comment if this formalism can be used to study decoherence as well?
Yeah, obviously, that's what I pointed out. The Loschmidt echo is a kind of decoherence which was studied for the same Hamiltonian and was published in PRL. Loschmidt echo, in fact, is a measure of the decoherence. We cannot directly measure decoherence with the help of quantum speed limit time of non-Markovinity, but yeah, from the same procedure, we can measure Loschmidt echo, and Loschmidt echo measure decoherence.
Okay. And another question is, can you please briefly explain how you can compute non-Markovianity due to pure dephasing?
This is, I would like to refer to the equation back for non-Markovianity where it was one slide back. Yeah, this one. This is a quantifier for measuring non-Markovinity. Okay, like I pointed out before, in this quantifier, there are two conditions. The first one is the pair of initial density matrices, which maximizes this integral. And for a dephasing environment, this pair is in fact the this pair of density matrix correspond to the plus minus basis. And for bosonic environment, this pair corresponds to the computational basis, to the density matrices of computational basis. That is a difference between dephasing and relaxation environment. So if you are using dephasing environment, this pair of density matrix you have to use, which correspond to the plus minus basis. And if you are working with a bosonic environment that impose relaxation processes, then this pair of density matrix correspond to the two computational bases of the qubit.
Okay. Thank you. So, I mean, just a little bit question regarding this. So, of course, this involves the maximization. So, did you use any, special protocol for finding the maximum of this N of t?
This has already been proven in a paper which I can, for that I would need to minimize my slides, but there is a paper in which a lot of work has been done on the two sides, that is for bosonic environment and for fermionic environment, and it is verified that for bosonic environments, the maximum, like I said, the initial density matrices again correspond to the computational basis. So we can do that in Mathematica, and for one case I have done that.
Sorry, Dr. Salman, I can't hear you. Is your mic okay? I think Dr. Salman might have some connectivity issue.